Well, here we are at the final video for Unit 5B, where we will look at the connection between energy and capacitors. So make sure you've got your notes ready, your video pausing and rewinding mouse clicker ready, and off we go. Now, capacitors store charges, and charges are basically little bundles of energy, which is kind of a rough definition, but it works for what we're talking about here. When we think of charges then in this way, as little bundles of energy, it's easy to see that capacitors store energy. We can think of them as potential energy storage devices. Now, we've seen that a practical way of charging a capacitor is to attach its plates to a battery. Charge then flows from the battery through one plate of the capacitor onto the other plate and then back to the battery. This leaves one plate with a positive charge and one plate with a negative charge. To accomplish this, the battery must do work to transfer that charge. This work, remember, is just a transfer of energy. This work increases the electric potential energy of the capacitor. A charged capacitor then stores energy as electric potential energy. Now, to find out how much energy is stored in a capacitor, we have to recall that a charge moved through some potential difference gains potential energy by U equals QV. Now, in charging a capacitor, lots of charge is moved from the negative plate to the positive plate. At first, when the capacitor is uncharged, the potential difference is 0 volts. When it's fully charged, it has the same potential difference as the thing that charged it. That is, the potential difference starts at 0 volts and increases to some amount greater than 0 volts. On average, the potential difference across a capacitor while it's being charged is half the total potential difference when it's done being charged. Therefore, the potential energy stored in the charged capacitor is 1/2 QV, where Q is the charge on the capacitor and the delta V is the potential difference. Now, it's not hard to see that there are some things that we can do with this. Remember, though, that although we are focused primarily on parallel plate capacitors, this works for all capacitors. First, we know that charge is related to the capacitance by C equals Q over V. Now, we can rearrange this to get Q equals CV. And we can plug this into the potential energy equation to get this right here, which simplifies to the potential energy is equal to 1/2 CV squared. So we have two equations we can use then for potential energy stored in a capacitor. U equals 1/2 QV and 1/2 CV squared, where electric potential energy of a capacitor with charge Q and potential difference delta V. And this is the form of the equation that you're going to see on the AP equation sheet. And the potential energy stored in a capacitor then depends on the square of the potential difference across it. And this result is kind of reminiscent of the potential energy stored in a spring, which was 1/2 kx squared, if you remember. A charged capacitor is really analogous to a stretched spring. A stretched spring holds the energy until we release it. Then that potential energy is transformed into kinetic energy. Likewise, a charged capacitor holds electrical energy until we discharge it. The usefulness of a capacitor stems from the fact that it can be charged very slowly over like many seconds and then released that energy very quickly. A mechanical analogy would be using a crank to slowly stretch the spring of a catapult, then quickly releasing the energy to launch a massive rock. So just where is that energy in the capacitor stored? Well, it's stored in the electric field of the capacitor. Charging a capacitor stores energy in that capacitor's electric field as the field grows in strength. Later, when the capacitor is discharged, the energy is released as the field collapses. Well, that about does it for Unit 5B. From here, we're going to move on into circuits. We'll see you in class.